What is going on, everyone? Welcome back to another video. Today we are going to be doing a Fluent tutorial, the lid-driven cavitation. Let's get into it. So what is lid-driven cavitation? Well, it's a very famous CFD problem that is used for validating numerical methods and investigating the fundamental behaviors of incompressible flows in enclosed spaces. The problem is that we have a fluid inside an enclosed space that is surrounded by three stationary walls. The top wall is dragged towards the right or moving to the right with some velocity. It swirls the fluid around in the cavity, forming a vortex in its center. This is what we call the primary vortex. Now we can see that as the Reynolds number is increased, there's the formation of these secondary vortices at the cavity's corners. This is formed because of the fluid being pushed against the stationary wall, resulting in a change in flow direction due to the no-slip boundary condition. Now, what does it mean by increasing the Reynolds number? This simply means that we're increasing the velocity at which the top wall is moving. Because as we know, the Reynolds number is a function of density, velocity, length, and viscosity, and we're keeping all the other terms constant. So to increase the Reynolds number of the fluid, we are simply increasing the speed at which the top wall is moving. Evidently, the governing equations for this problem are the Navier-Stokes equations, which simply say that the advection of the fluid is equal to the negative of the pressure gradient in that direction, plus the viscous forces, plus any external body forces, which means any gravity, electromagnetic forces, etc. So how are we going to solve this problem in Fluent? Well, we're going to initialize a fluid area of a 1 by 1 meter cube. And these three walls here, the left, the bottom, and the right wall, are all going to have velocities of 0 because these are going to be stationary walls. And our top wall is going to simply have some velocity in the x direction and no velocity in the y direction. We are going to initialize our fluid domain or a cavity with water, which in ANSYS has these properties, a density of 998.2 kilograms per meter cubed, and a viscosity of 0.001003 kilograms per meter second. And we're going to solve this problem to have a Reynolds number within our cavity of 1,000, which, as I mentioned before, if we know the relationship of the Reynolds number, which it is the density times the velocity times the length of our domain divided by the viscosity. If we rearrange this, we can get the velocity of our top wall that we need in order to get the Reynolds number of 1,000, which in this case can be calculated to be 0.001 meters per second. And going back to the first slide to see if the results that we're going to get are correct, we should see, based on this figure right here, that we are going to have the formation of a vortex in the center here with the formation of two secondary vortices, one bigger one in the bottom right corner and a smaller one in the bottom left corner. We will not be seeing this formation of the third vortex up in the top left corner that only occurs when we increase the Reynolds number to a higher amount, as we see in these figures here. So from Fluent, based on the parameters I showed on this slide, we should be able to validate the results and pretty much get the same results as we are seeing in the figure here. So let's jump into Workbench and let's get into building this simulation. Now with Workbench open, we can go ahead and start building the simulation. In the middle here, I have my project schematic. This is where we are going to be building the simulation. And on the left-hand side here, these are where I have all of my analysis systems. And for this particular simulation, I'm going to go ahead and get the fluid flow Fluent analysis system and drag it into my project schematic. And as we can see, we have a whole bunch of question marks here, which are the different steps that we have to go through in order to solve the simulation. So the first thing that we're going to start with is initializing the geometry, which is that 1 by 1 meter squared that I presented in the slides earlier. So let's double click on geometry. And we can see in the bottom left corner, it says starting SpaceClaim. So I'll wait for that to open. Now SpaceClaim open, we can go ahead and start building our geometry. By default, ANSYS has us sketching, or SpaceClaim has us sketching on the ZX plane. I prefer sketching on the YX plane because it just makes it better or easier to initialize and apply boundary conditions later on. So to start, I'm just going to go ahead and press on and sketch editing up here. And the first thing that we're going to do before we start building our geometry is that I'm going to make sure that the SpaceClaim environment is using the correct units. I want to be using units of meters because later on in the simulation, everything is basically in meters, seconds, and kilograms. So it's just going to make it easier when I sketch my geometry that I'm using the correct units and just make everything a little more consistent. So in order to do that, I'm going to go up here to File, and I'm going to press on SpaceClaim Options. And this is going to open up this window here. If we go to Units down here, we can see that right now I have length set to millimeters. I'm going to change this to meters. And again, this is just to make it more consistent throughout the whole design of the simulation. So I'm going to press on K to change the units. And now let's go ahead and sketch our geometry. So in order to create a sketch in SpaceClaim, we're going to press on Sketch Mode. And then we have to choose a plane on which we want to sketch on. So I want to sketch on the YX plane. Here's the ZX plane like before. So YX plane, I'm going to click. I'm going to press on the Z axis here to make it normal to the screen. So it's easier to view. And I'm going to choose the rectangle command. I'm going to click it or snap it to the center of my origin. And I'm going to drag out this square. And you can see that there are two dimensioning lines. This is where I can type in the dimensions that I want. So I'm going to go ahead and press on 1 meter to make the dimension of the first length. And then I'm going to press on Tab to go to the other dimensioning line. And I'm going to input 1 and then press on Enter. And this should give me a 1 by 1 meter cubed like this. And so if I press on End Sketch Editing, this is going to create a surface of a 1 by 1 meter square. And this is it for our geometry. It's a very simple geometry. It's a 2D surface because we're running a 2D CFD simulation, and there's only fluid within our little cavity that we've initialized to be a 1 by 1 square. So now let's move on to the meshing stage. So I'm going to go ahead and close on SpaceClaim here by pressing the big X, and we're going to return back to Workbench. And as we can see, we have a check mark now beside geometry. So that is ready to go. So next up is the meshing of this geometry. So we can double click on mesh, and down in the bottom left corner, it says starting meshing. So I'll wait for that to load. Now with the mesher open, we can go ahead and start constructing the mesh for this simulation. So to start, I'm going to go ahead and build the default mesh that ANSYS will create for the geometry that we have here. So to do that, I'm going to right click on mesh, and I'm going to go to generate mesh. And this is going to only take a second. And we can see that it's created a mesh for this geometry. Now, this mesh is fairly coarse. For this simulation in particular, it probably would be able to accurately depict the big vortex, the primary vortex that will occur in the middle, but it's way too coarse for it to capture the smaller vortices in the corners here. So I'm going to go ahead and just make the overall mesh a little more refined in order to capture these finer details that we're expecting to see in the corners of the cavity. So to do that, I'm going to add a sizing, and I'm going to right click on mesh again. I'm going to go to insert and press on sizing. Now, by default, we can see that ANSYS has these two yellow fields, and this is because it's missing information from the user in order to properly handle the sizing and to update this mesh to a finer size. So we can see that it's missing the geometry and it's missing the type of element. When we select the geometry, we'll be able to change any of the fields down here afterwards. So let's go ahead and do that. So I'm going to press on the face selector tool up here, or by using Control F. And I'm going to choose the one face that we have, our geometry here. I'm going to press on no selection, and we have an apply button that appears here, and I'm going to press on apply. And now we can see that by default, the element sizes were 0.070711 meters. And this was too coarse for our liking. So I'm going to go ahead and enter a smaller number for our maximum element size. And I'm going to use 0.025. Now with that, we have no more yellow fields. it has all the information that it needs in order to properly handle this sizing. So I'm going to go ahead and regenerate the mesh by pressing on mesh, right-clicking on mesh, sorry, and pressing on generate mesh. And we can see that the mesh is a lot more refined than it was. It's still pretty coarse, but it will be able to capture the finer details for the little secondary vortices that are going to occur in the corners of our cavity. So next up, we're going to create some name selections in order to specify different aspects of this geometry. And this will be easier later on in Fluent in order to initialize and implement our boundary conditions. So to do this, I'm going to go ahead and start with the face selector tool that's already selected here. I'm going to press on the face. I'm going to right click and go to the bottom here and press on create named selection. And so I'm going to name this the fluid domain. Press on OK. So now we can see that we've created a name selection here. It's added a little branch to the project tree. I'm also going to create name selections for the 4 walls. So I'm going to go ahead and press on the edge selector tool this time. And I'm going to click on the top wall here. I'm going to right click and press on create name selection. And I'm going to call this the moving wall. Press on OK. And I'm going to do the same thing for the stationary walls. And since all the 3 stationary walls have the same initialization, I can go ahead and group these together by holding Control and pressing on the 3 edges here. Right click and press on create name selection. And these are going to be my stationary walls. So now that we've added these name selections and we've created our mesh, we can go ahead and move on to Fluent in order to continue initializing the solution, creating our boundary conditions, and run the simulation. So let's go and do that. Let's close the mesher. And now we can see that we have a lightning bolt beside mesh. Now, what does this mean? Well, it means that we've created items within the mesher that have not been able to be translated to the next step of our problem here. And this is generally caused by when you create name selections, they don't automatically get transferred through the data of the simulation. Generally, when you generate the mesh, they do. So easy fix, all we're going to do is right click on mesh and we're going to press on update. And this is going to ensure that all of the information that we've created in mesh is going to be transferred through the various lower modules of this simulation. So as you can see, we have a check mark beside mesh now. And so we can go ahead and double click on setup to start up Fluent and initialize the boundary conditions. Upon double clicking on setup, we are met with the Fluid launcher, and there's a couple things that we need to initialize before going into Fluent. The first thing would be dimension, but since we've built a 2D geometry, it knows by default that we are going to be running a 2D simulation, so we can't actually change this, but we want to keep it 2D, so that's good to go. We are going to change the double precision and put a check mark to use double precision for this simulation. And now for the solver processes, I'm going to put this to 2, and in parallel settings for solver GPUs per machine, I'm going to put this to 1. And these are dependent on your local machine that you're running ANSYS on, but 2 solver processes and 1 GPU are very standard for any computer. So I'm going to go ahead now and press on start to launch Fluid. Now with Fluent open, we're going to go ahead and start initializing this problem. In the general section here, we're going to leave all of these solver settings the same. The first thing that we're going to go change is here on model. So if we double click on model, we are going to change the viscous model to laminar. So we're going to double click on viscous, and this is going to open up this window here. And we are going to click on laminar and press OK. So now our models are correctly set. We are performing a viscous laminar simulation, and we're going to keep the energy equation off. For materials, as we mentioned before, we want to use water for this simulation. So in order to get water, I'm going to press on the plus beside materials, press on the plus beside fluid, and I'm going to double click on air. And this is by default going to open this window where we have the properties of air. But if we press on Fluent Database, it's going to open up this window. And now these are all of the fluid materials with different properties that are by default in ANSYS. And we are going to scroll down to the bottom and find water liquid here. And we can see that it has these material parameters. And to add it to our project, I'm going to press on copy. And we can see on the tree here, it added water liquid to the tree. So that's good to go. I'm going to press close, and I'm going to close this as well. In cell zone conditions, this is where we initialize our fluid area with the type of material that we want to use. So I'm going to double click on fluid zone conditions. And here we can see that we have now our named selection that we created during the mesher. So I'm going to click on fluid domain and press on edit. And now by default, we can see that Fluent is running air for our fluid domain. But since we've added water to our materials tree, I can press on this triangle here and change the material to water. So now we have initialized the fluid domain to be water instead of air. So I'm going to press on apply. And I'm going to close this window. Next is the boundary conditions. So our boundary conditions for this problem, as we saw before, we have 3 stationary walls being on the left, bottom, and right side here. And we have the top wall moving with a velocity of 0.001 meters per second in order to get a Reynolds number of 1,000 with water. So I'm going to double click on boundary conditions. And again, you can see that we have our different name selections that we created during our mesher stage. Interior fluid domain was one that was automatically created, but we don't have to worry about that one. So I'm going to press on moving wall because this is the first boundary conditions that we're going to implement. And I'm going to press on edit. And this is going to open up this window here. And before we continue, I actually forgot to mention that we can see that the type here is wall, and we have different types of boundary conditions that we can use for different CFD problems. But again, we want to use the wall parameters. So it's good that by default, it was initialized as a wall. And by default, we have it as stationary wall. This is not true. We want the wall to move. So I'm going to press on moving wall, and it's going to add some fields here to implement. The wall is going to be moving in the X direction. So we want to put this as 1 and keep the Y as 0 because we don't want any movement in the Y direction. And I'm going to put a speed here of 0.001 meters per second, again, to get a Reynolds number of 1,000. We want the no slip boundary condition, so that is good. And we want translational wall movement, so that's also good. So we can go ahead and press on apply. And we can close this window. And we'll do the same thing with the stationary walls. So we can see that the type is wall here, and we're going to press on edit. And we can see that by default, it's running a stationary wall with the no slip boundary condition. So that's good to go. And so next up, we're going to go ahead and look at the residuals module in order to ensure that the solution is going to converge to a proper solution with not too much error. So to do this, I'm going to press on the plus beside monitors, and I'm going to double click on residuals here. And we can see that by default, the absolute criteria shows that once the residuals fall below 0.001, it's going to say that the solution has converged. I want to get a little bit more of an accurate reading because this is a pretty stable simulation and doesn't require a lot of computational power. So I'm going to go ahead and change these to 1e to the -6. And I'm going to put these for all the residuals. And then I'm going to press on OK. So that is now good to go. Next up, we're going to initialize the solution. So I'm going to double click on initialization, and we're going to use a standard hybrid initialization. So hybrid initialization and press on initialize. And in the console window, we should see that it is going to initialize our problem. So now we can see in the console window, it says hybrid initialization is done. So we can go ahead and run the simulation. But before that, I actually remembered I forgot to change the method that we're going to use in order to solve this simulation. So I'm going to double click on method, And instead of using a couple scheme, I'd rather use a simple scheme. So I'm going to go ahead and just press on the tree here and change it to simple. And now since we've changed the method that we're going to use to solve the simulation, I'm have to reinitialize the simulation. So I'm going to go to hybrid initialization and initialize. Current data has not been saved, including solution data and any report files, animation files, etc. Do you want to discard the data and proceed with the initialization? Yes, I do, because I didn't actually run the simulation and get any results. So again, we can see in the console window that it says hybrid initialization is done. So we can go ahead now in this time and run the simulation. So I'm going to click on run simulation or run calculation, sorry. And I'm going to put 1,000 as the number of iterations in order to try and get a better convergence so that the residuals drop below 1 to the -6. So we can go ahead and press on calculate. And as we'll be able to see in the console window, it will start writing all of the different iterations it is going to do. And we are waiting for a done message like it does for hybrid initialization. So we'll wait for that to load. Hey guys, welcome back. We can see that the simulation has now loaded. It says calculation complete. So we can go ahead and press on OK on this message, and we can move on to the post processing in order to see different contours and streamline plots for the results that we calculated for this lid-driven cavitation problem. So I'm going to go ahead and close Fluent. And are you sure you want to quit this application? I am sure. So we're going to go back to Workbench. And now you can see that we have a check mark beside setup because we are able to set up all the boundary conditions, initialize the simulation, and run it in order to get some solution. So let's go ahead and double click on results to launch post processing. As you can see, it says starting CFD-post, so I'll wait for that to load. Now with CFD-post open, let's go ahead and visualize the results that we've obtained. So I'm going to press on the Z axis to make this normal to the screen. And let's start with the streamline plots as we saw in the image in the slides. So I'm going to go ahead and press on the airfoil up here that has some streamlines going around it. I'm going to name this streamline 1. That's okay. For the start from field, I'm going to go ahead and select fluid domain because we want to see what the results are going to be within our fluid domain. And for the variable we want to see is velocity, so that is good. And I'm going to set these to 50 streamlines. So I'm going to go ahead and press on apply. And as you can see, this is the streamline plot for the solution that Fluent has calculated. A couple things to note based on this streamline plot in order to validate the results that we're obtaining is that the solution is respecting the boundary conditions that we inputted in the Fluent solver. On the top wall here, we have a velocity of 0.001 meters per second, and this was the exact velocity that we implemented in order to get a Reynolds number of 1,000. We can also see that we have the creation of the center or primary vortex as we saw in the slides. We don't necessarily see the other or secondary vortices in the bottom corners, and this is because we need to implement more streamlines in order to see it. So I'm going to go ahead and change this to 100 streamlines and press on apply. And as you can see now, by adding more streamlines, we see that there are, in fact, secondary vortices in the corners of this cavity, which is consistent with the results that we saw in the PowerPoint at the beginning of this video. We know that at a Reynolds number of 1,000, we also didn't have the creation of this upper secondary vortex in the top left corner, further validating the results that we've obtained. And you can go ahead and change the number of points to say to 200 streamlines and press on apply. And you can play around with how you visualize these results to get different graphs. So by adding more streamlines, we can more easily visualize these secondary vortices that are occurring in the corners of the cavity. These vortices will always be a little harder to visualize, and we do need more streamlines to visualize these since the fluid flow is not moving very quickly in these areas as compared to the rest of the cavity. So another thing that we can do is we can visualize the pressure distribution and velocity in specifically the X or Y direction in different contours. So to do this, I'm going to press on the careful map here that says contours. And let's create contour 1. That is good. And for the location, I'm going to change this to symmetry 1, which is going to represent our fluid domain here. And I'm going to keep the variable as pressures because let's visualize the pressure for this problem. I'm going to change the number of contours to 20, but this just changes the amount of colors that you can have in your plot. So the more number of contours you have, the more smooth the gradient of colors is going to be on the visual. So I'm going to go ahead and press on apply. And we are going to click on the checkbox beside Streamline to unvisualize the streamlines. And so we can only see the contour plot that we've created. And as you can see, the results that we've obtained are fairly good due to the movement of the upper wall in the X direction with some velocity and the no slip boundary condition. This is causing the flow to circulate to this area, causing an area of higher pressure. And as a result, the only way that this flow can escape is downwards. So this is what ends up causing the swirling motion that we saw within the streamlines. If we wanted to visualize, say, the velocity in the X direction or velocity U, we can change the variable to that, press on apply. And we can see again, the solution is respecting the boundary conditions that we implemented, having a velocity of 0.001 at the top here. And we can see that in the top half of the cavity, the velocity is going in the right direction. And then when it swirls back to the bottom half, we can see that it's going to the left direction with these negative numbers here. We can also visualize the Y direction velocity or velocity V by pressing on apply. And again, it's a similar story here. With the negative velocities, we can see that this fluid is moving downwards, which is the start of the swirl because of the higher pressure here. And the only way for the fluid to escape is by going underneath. And we can see that the velocity of the fluid in the Y direction is moving upwards on the left-hand side of our cavity here. And I know I've just been changing the variable that we've been showing for this one contour, but if you wanted to create all of your different contours and switch between them, you could do that as well. So just click on contour again, and that's going to create contour 2, and you can name this to whatever you want, but I'm just going to press on OK. And now we're in the details of contour 2, so I'm going to go ahead and show the pressure, press and apply. And now we're showing the 2 contours, so I'll deselect the first one, which was the velocity in the Y direction. And actually, for contour 2, I needed to change this to symmetry 1 for it to be on the correct plane. Now I'm going to press on apply, and now we can see that pressure plot that we saw earlier. And I can switch between them now by pressing on the check mark beside which contour we want to visualize. And the same thing for the streamline. If I want to go back to the streamline, I can press on the check mark beside streamline, and now we have our streamline plot back on the screen. Now that we were able to visualize the different variables for this problem and perform a results validation, we can conclude that the results that we've obtained from the simulation match the expected results that we presented earlier in the PowerPoint. And that is it for this simulation. Don't forget to like the video if you guys thought it was helpful and subscribe for more engineering content.